Okay, enough of the introduction. Now, let's take a look at example by examples on how to do Monte Carlo simulation. Okay, the core idea of Monte Carlo simulation is to repeat doing that and then make summarization. Okay, repeat sampling from the distribution and do the summarization. Right. The first example that we are going to look at in the Monte Carlo simulation is to do the integration. But we are going to do integration without really doing the analytical integrating. Right? We are going to do integration by using Monte Carlo simulation. How to do that? So first, we need to know the mathematical construct. We know that if you can plot a graph of a function like this graph is 1 plus psi t. Right? If you plot this graph, it looks like this one. And this graph have the height of m. You know that is 2 for this one. And the width of t, depending on the time that you want to capture, you want to do the integration. Like you can think of this as the limit of the integration from one point to another point. And then you are trying to estimate the area under the curve of this graph, right? So how to do estimation in this case, right? How to do that? In Monte Carlo simulation, we can do this by, suppose that I'm closing my eye here. Can I close my eye? And then pick one point, pick another point, pick another point, another point, another point. Right? Doing many times and then count the number of points that fall under, and I kind of sampling it throughout here, right? Repeating doing that using using uniform distribution. Uniform meaning having similar chance in both this axis and this axis, so that you can imagine that the point would spread out equally, right? And then comparing the point to the line. If it's under the line, then you count it as 1. If it's above the line, not counting it, right? Under the line, count it as 1, and keep doing that and divide by, you get the number n, which is the number of time that the point is under the line here, right? This point, this point, this point, and then divided by the total number of time that you sampling, right? The number of time that you try, right? And then you get the area under the curve. Think about that. If you kind of simulating the point throughout here, you have a lot of point clustering occurring under the graph, right? Occurring under the graph here, and that allows you to estimate the area under the graph, right? So let's jump to the code. Okay, then first let's take a look at the analytical equation first. Suppose that I'm integrating the function 1 plus psi t from t0 to 2 pi. So what will happen here? I'm integrating 1 plus psi t, right? Integration is linear operator. I'll put it in. I get this integration of 1 dt t, and from t0 to t0 plus 2 pi. And minus integrating the psi, you get minus cosine. The minus cosine from t0 to the plus 2 t plus 2 pi. And the result here, in summary here, you just substitute here in the first hand, right? Questions in this slide?
No, I want to precaution about the next slide, but I just make mistake.
Oh, sure.
The next slide that you said that it will be approximation pi, right? But it is the area. Just the next slide.
Yeah, it's approximation of 2 pi actually, right? It's approximation of 2 pi. For that, it should need to divide it by 2, and because here you can see that this is 2 pi. Thank you. So integration here is t0 plus 2 pi, t0 plus 2 pi minus t0, you get 2 pi. For the cosine, why is it 0? Can anyone tell me? y integration of cosine with 2 pi is 0 because when it's quiet, because of what? Correct. Actually, because the period, right? Sinusoidal is periodic, and the period is 2 pi. The graph itself is going up 1 and down 1, right? That means you calculate the total area under the curve for one period, you get 0. And that's why we get 0 here. So the result here is 2 pi. That means it's about, you use the pi constant, you get something like 6.283 something, go on, right? So that's the area under the curve. Okay, so this is analytical solution. Now we are going to estimate this without integration. So how to do that? All right, this is the code to perform Monte Carlo simulation in R. So what I'm doing here is to define a function, 1 plus sine x, and just for comparison. And then this run can be changed from small number of time that you perform to a large number of time, right? to like 10,000, 100,000. And to repeat a lot of time. The good thing about this example is that you can think about sampling in each time. They are independent. Actually, you can parallelize the process, but I did not do that, right? I just used the basic function, but you can imagine that you can just chop it into 100,000 pieces and then fetch into multiprocessor to let it compute. That would be faster. Like if you use Python, you use NumPy, it will parallelize the process there, right? And this as well, this is kind of parallel, is a bit. So you have generate using R uniform for T, right? So basically here, what we are doing for T and Y is to generate the order pair, T and Y. So for T here, you get n equal run, start from 2 to 2 plus 2 pi. And for this Y is also run and from 0 to 2. Right? Why is that? It's because of this 0 to 2, and then I'm simulating it up here and down here, meaning that I'm kind of getting the point inside this green box. Right. After that, fetching t into the function, you get ft. Yeah. Ft is the I would say it's the line here, the yellow line here, not yellow, actually orange line here. Then we are going to compare the orange line with the y value. If the y value is above, we will just ignore that. If the line, if the value is above the line, we will ignore that. If the values are below the line, right, we will include that into the count. Usually I teach this to master degree students 12 years ago. That's the first time I teach this one. I kind of dumb it down to be a simpler version here, so that everyone can study that. Right. This is the approximation of 2 pi. Approximation of 2 pi. Okay, just change it in your code. Thank you. I will correct it for the afternoon session. All right, so putting it in here, oh, it's gone somehow. Right, so this is the comparison. If y is less than ft, that means it's under the line. We'll count it, right? We'll count it, and then divide it by the number of run, and multiply by the 2 pi times 2, right? Why doing that? Because if we now go back to this one, the number the number of point for the number of point that is that are in number of point is in this region, in the blue region here, comparing to the total number of run, it will give you the proportion, right? The proportion of point that falling in under the line, that falling under the lines, and that is actually the percentage of the area under the curve. You need to have the total area, and then multiply that to the total area. You get the estimation of the area under the curve here. So here, yeah, and this is just plotting. I'm plotting the comparison between the two using geom point, geom path. Right. Let's jump to the to our program. Right. So here, the result. The first one. Here, I'm going to just select all of this. Let's start with run equal one run. If I use just one run, meaning that I use just, I will just sampling one number, right? And then compare just one number. That means it would estimate this. Oh, why is that? Right, it can now estimate this. Is 2 pi time 2, right, time 2. Sorry, again. Right, it's estimated to 12 something, right? It's 2 pi times 2. And because this is 1 or 0, now if we increase it to 10, the value is 3.76, 8.79. Actually, I should just simulate the above here. Right? It's 8 something, 5 something, 8 something, 8 something, 6 something, right? You can see that the values kind of fluctuate when we get only 10 runs. Now let's increase it to 100 runs. 100 runs and then run this. Now we get about 6 point something. You can now see that the value still fluctuates a bit in every run, right? But the fluctuation decreased, right? From 3 to 12 to something that really wide. Now you have the estimation that is really close to the value of 2 pi, which is 6 something, right? Okay. Now if I increase this to 1,000, run it again. You can now see that the fluctuation occur in the decimal places instead of in this unit. Okay, if I increase it further to 10,000, then it becomes stable at the 2 decimal places. Okay, if I increase it to like 100,000, a million, let's increase it to that million. You get to 6.285, 6.288, but 6.28 for sure, right, for the 2 pi. And now if we go back to the slide, the result is 6.28 something. You can see that increasing the number of times that it trial will get your result more precise to the values. This is the basic of Monte Carlo simulation, which is part of your lab that you have to do. Right. So you have the code, you can modify it first. So let's take a look at what happened in that. Okay, if I use n equal 10 for the graph and then for the point here, I got the area under the curve equal 8.2 7. So this is just for one time trial. 8.7962 and got the points here under the curve, right? If I increase the number of n to 50, right, this becomes 7, right, close to 6.28, and you get the point here under the curve and the point above the curve as well, actually, but they don't show here. At the n equal 100, get 7 something, n equal 500, n equal 1000, n equal 5000, n equal 10,000. You can see that now the points are packed in under the lines, and when you divide by the total number of points on the line by 10,000 and then multiply with the total area, you get 6.2868. And to just show what happened, you see the convergence in the value of estimation, right? When you increase the number of iterations. So you might ask in your lab, because I asked you to try out a number of level of iterations. If you try to add 10, what values should you report? I would leave it to you because it doesn't matter. It would not be accurate, except if you are lucky. Right? But in reality, it will just kind of fluctuate all over the places. And yes, for example, this one is to get something like almost 9, and then it could approach these values. If you try it many times, you get the value quite stable there, right? So this is the first example of Monte Carlo simulation, right? Any questions first about this Monte Carlo simulation? Any question here? And this is also part of your lab. So you can see that what we are doing here is to be sampling using uniform distribution through all of this, and then look at those that are following the mathematical construct, like a comparison. If it's less than that, count it, and then we get the values. Okay, so Monte Carlo simulation can be used to do integration. This is very simple integration. Why using this? Because you can have examples that have complicated integration, like integration of 5 variables. Instead of doing integration by hands, you can use this and then just sampling it through, right? And then you can estimate the integration without really have to integrate in distance. Okay, right? We have questions coming in. Could you explain the code in example 1? Sure. Right, let's start with this. Because we want to get the number of points under the line, right? What we need to do is to sampling for the point in the square region. So what I'm doing here is to, for T here, is to the random of the uniform distribution with the number of run here as n, and minimum at 2 and maximum at 2 plus 2 pi. Right, so this means that I sampling the t axis, right, the x-axis, and then I did sampling the sample the y-axis, right? Sample the y-axis, and then after that I will get something like the order pair of t and y. Right? The order pair of t and y. I use t to calculate using function, meaning that for every t there will be the value f. So comparing to the graph here, what I did is to get the point throughout this rectangle, and then if it's below this orange line is this ft, then I would count it, right? So sum here would convert the comparison from true and false into 1 and 0. If it's true, it will be 1. If it's false, it will be 0. Then divided by the number of runs, you get the proportion, and multiply by the 2 pi times 2, then you get the area. The question is, okay, yeah, right. Number of random point, correct. So that is how this works, right? Let's move on, seeing more examples. I think that will make you more understand to the concept. And also doing your lab, that will also increase your skill. Okay, we have more questions coming in, I think. No, it's explanation from the PA.
Actually, it's not creation. I just try to clarify
Yeah.
module by module.
Thank you.